Acid-base is felt to be a confusing and often intimidating subject, despite the fact that it is simply the maintenance of a normal hydrogen ion concentration. Homeostasis and optimal cellular function requires maintenance of hydrogen ion concentration of body fluids within a very narrow range. To maintain this crucial balance of acid and base in the fluids, the body either adds or removes concentration of hydrogen ions within the blood. The balance can be disrupted by pathological conditions such as infection, inappropriate medication use, trauma, and etc. We will go over some important concepts first. An acid is a substance that donates or gives up a hydrogen ion in solution. Some examples are acetic acid. Another is hydrochloric acid, which is in stomach to help with digestion. Non-volatile acids such as lactic acid, hydrochloride, and phosphoric and sulfuric acids must be metabolized or excreted in fluid. In our lecture, however, we're going to focus more on carbonic acid, H2CO3, which is usually identified as carbon dioxide, and it is more related to our learning of acid-base. It is a volatile acid that is eliminated from the body as a gas. H2CO3 is metabolized in the cell, producing water and carbon dioxide. The carbon dioxide is then eliminated through the lungs. A base is a substance that accepts a hydrogen ion in solution. The major base in the body is bicarbonate, HCO3. Solutions with more acid than base are acidic, and solutions with more base than acid are basic. We know that the body makes more acids than bases. Acids and bases can be strong or weak, with the exception of a couple. Most in the body are weak. Sources of acids include those from byproducts of normal metabolism. Remember how glucose in the cell is oxidized and oxygen is reduced to form water and carbon dioxide as byproducts of cellular respiration? Well, carbon dioxide is considered to be acid because of its relationship with carbonic acid, the compound which transports CO2 to the lungs so that CO2 can be eliminated out of the body. I'll let you review the rest of the acids mentioned in your slide. Just keep in mind that if cell destruction were to occur, intracellular acids would be released into the extracellular fluid. Sources of bases include sodium hydroxide, NaOH, which is a strong base and binds with hydrogen ion readily. Ammonia, NH3, is another strong base formed during normal protein breakdown. It traps hydrogen ion as ammonium, NH4+, to eliminate the hydrogen into the urine. Aluminum hydroxide, LiOH3, and bicarbonate, HCO3, are weaker bases and bind with hydrogen ion less readily. However, although bicarb is a weak base, it prevents major changes in body fluids pH. Well, there is a reason for long-derived formula for pH. Knowing that the unit of measure for normal plasma hydrogen is 1,000,000 times smaller than the unit of millimoles for sodium or potassium, no wonder a scale had to be used. Like earthquakes, hydrogen ions are measured in logarithmic scale, and concentration is measured to a corresponding pH. The normal hydrogen ion concentration in plasma is 40 nanomoles per liter. It corresponds to a pH of 7.4. Interesting, right? Well, just like fluids and electrolytes, acids and bases are constantly produced in the body. They must be constantly regulated to maintain balance. Remember, only free hydrogen ions are physiologically active. Hydrogen ions bound to other atoms or molecules is inert. Free hydrogen ion is destructive and associated with severe consequences to cell structure. See the importance of this balance? The respiratory and renal systems are active in regulation of carbon dioxide and bicarbonate, and they are crucial in the balance. So we might not know how to calculate the negative logarithm, but at least we can understand that pH is defined simply as the negative logarithm to the base 10 of the concentration of hydrogen ions in solution, right? Just kidding. All we need to understand is that pH is a measure of hydrogen ion concentration. So does the pH scale measure free hydrogen ions or bound hydrogen? What do you think? It measures free hydrogen. An increase in hydrogen ion concentration is indicated by a drop in pH, and it is known as acidemia if the plasma pH is less than 7.35. A decrease in hydrogen ion concentration is demonstrated by a rise in pH, and it is known as alkalemia if the plasma pH is above 7.45. Again, pH measures the degree of acidity or alkalinity. It is inversely related to hydrogen. To ensure homeostasis in the body, all fluids must contain balanced quantities of acids and bases. Any changes from the narrow limit cause significant disruption to body functions. We know a pH of 7 is neutral, but the normal value for humans is between 7.35 and 7.45, which tells us that we are actually slightly alkaline. We are no longer compatible with life if our pH drops below 7 or goes above 7.5. Okay, review time. A pH of less than 7.35 represents high or low hydrogen ion concentration. Review time. A pH of less than 7.35 represents high or low hydrogen ion concentration. High, and it is known as acidemia or alkalemia. Acidemia. A pH of more than 7.45 represents high or low hydrogen ion concentrations. Low, and it is known as alkalemia. Here are some helpful reminders. More acid is the same as more hydrogen ions, which is the same as lower pH. Less acid is less hydrogen ions, which is a higher pH. It is an inverse relationship. Where the acid goes up, the pH will go down. More base or bicarbonate is the same as a higher pH. Less base or a lower bicarbonate is the same as a lower pH. Wherever the base goes, the pH will follow. And a different type of helpful reminders. Wow, by now you have it memorized. Because hydrogen ion is so reactive, tight control of its concentration is essential. Most enzymes function only with a narrow pH range. Acid-base balance can also affect electrolytes, such as sodium, potassium, and chloride. Remember what electrolyte leaves the cell in acidemia? Potassium, right? And what ion does it exchange with? Did you say hydrogen? That's correct. It can also affect hormone. Do you remember what is given to get potassium back into the cell? Hopefully you said insulin, and in turn, that lowers the hyperkalemia. Don't forget that in this case, glucose is given as well. It is important to understand that to maintain the balance, the body will, if at all possible, attempt to adjust an acid-base change to move pH towards the normal range. So the initial change in either acid or base will be followed by a compensatory change in the other. Where there is an action, there's always a reaction. This means excess acids or bases will be neutralized in some way to protect the cells. And this will take us to our next topic, how pH is regulated to maintain balance.